Once again, good morning. Good morning to all those who are present here in this room, as well as all those who are present online. I was very happy to see that so many people are attending online, more than about 75 people are attending this session online, and really happy to see that so many students are also present here in this room. I'll be talking about photonic crystal fiber-based surface plasmon resonance biosensors, and how many of you, just to take an idea, how many of you are from BTech? BTech and masters, PhDs? Anyone who is specifically working in this area, photonic crystal fibers or surface plasmon-based? Okay. So we have started working in this area from last, specifically I talk of biosensors, then we are working in this area from last around 7-8 years. And before that, photonic crystal fibers, we have worked for about 20 years, about 20 years now. And initially we started with modeling, and then we have also got some of our fibers fabricated with the help of our collaborators. I come from Manipal University, Jaipur, and it is a part of Manipal Group, which is having 3 universities in India, and then there are 3-4 main campuses in various countries like Malaysia, Antigua, Dubai, and all. So basically, this group is majorly known for its medical education, and in Malaysia, it is said that out of every 4 Malaysian doctors, there is one who is passed out from Manipal. This is the beautiful campus. This is another view. The previous view was actually the view of main administrative building, and this is hostel side view of hostel blocks as well as main administrative building. I have a lab there which is known as Photonics and Optoelectronics Research Lab, and this is my Optica chapter. We have around 80 members, a little more than 80 members now in our Optica chapter, and they are very active, doing various activities in this chapter. This is a group photograph of one of the annual lunch that we have at a resort which is close to our university. As Professor Singh mentioned, that we are also working in a project which is quantum satellite and fiber communication. Our part is fiber part in that project, and we model optical fibers which are used for intercontinental satellite communication. We are partnering with the 3 other universities, major universities. Our PIs are from KwaZulu-Natal, Durban. One PI is from PSUTI Samara, and one PI is from USTC Shanghai. Besides that, we also have partnered with internally within India with the MNIT Jaipur. Professor Ghanshyam Singh is there. Then Siri Pilani also we are partnering. There are 11 partners on Russian side, and there is one partner on South African and Chinese side. There are partners on the other countries. Well, so I'll be talking about first photonic crystal fibers. Basically, how many of you are familiar with fibers, the technology? There is a core, there is a cladding, the light travels in the core, and then this is how the communication happens. Majorly, we know optical fiber for communication, but there are a lot of other applications where optical fibers can be used. So I'll be talking specifically about photonic crystal fibers. So photonic crystal fibers they look like this. As you can see in this diagram, there is a structure, and this outer structure, this acts as cladding, and then this inner region, it acts as a core. So actually here the total internal reflection mechanism happens like this. In case of conventional optical fibers, we know that the cladding has a little bit lower refractive index in comparison to core, and then the light goes on traveling within the core due to total internal reflection mechanism, which is governed by Snell's law. In this, what happens is the material is a single material. It is all silica. And due to these holes, this particular region, which is here, its effective index goes below effective index of this region. So there are two things here, refractive index and effective refractive index. So due to these holes, the effective index of this outer region goes little bit lower in comparison to the core region, and the total internal reflection mechanism happens like this. Here in this case, you see that there is a different kind of photonic crystal fiber where there is a bigger hole in the center. Now, how does this propagation of light happens in this region? It happens due to, it doesn't happen due to total internal reflection mechanism. It actually happens due to photonic band gap mechanism. So what happens is band gap, you can just think of it like this, that if a particular structure has a band gap for say 900 nanometers to 1100 nanometers. So what will happen? Any light which is falling in this within this wavelength range will not be able to penetrate into the outer region. So if you are propagating the light in center, which falls in the photonic band gap of a particular structure, then that light will travel within the core itself. It will not be able to. So as you can see, it is all uniform and symmetric. The structure is uniform. Launched into the core. It is launched into the core, like conventional fibers. See, only in this core. It will not penetrate into the cladding region. Yes, effective refractive. It is. They are created to bring down the refractive index in comparison to. So these are two different kind of photonic crystal fibers. One is called as solid core, and other one is called as hollow core PCF. So this is a method which is most commonly used for fabricating the PCFs. So what is happening here is there are capillaries, and then those capillaries are arranged in this this way. So this is called as stacking, and then they are inside a preform, and then that is drawn at high temperature, depending upon what material you are using for creating these photonic crystals. There are certain problems which you can very well think of, that what can be the problems with this. There are problems of getting the holes skewed. There can be deformed holes. There can be several other things. But in this whole method is very controlled method. So that's why we are able to fabricate these. This technology is now very mature, and there are commercial photonic crystal fibers which are drawn using this stack and draw method. There are other structures also which can be made using photonic crystal fibers. There are other methods also which are used, but they are not so common. They are used for mainly experiments or research purpose. No commercial photonic crystal fibers are produced using these methods. So the advantage of photonic crystal fiber is that they are endlessly single mode. What endlessly single mode means is that what happens in case of conventional optical fiber. If you look at this expression, this V is called as normalized frequency or V number. So if this V number remains less than 2.405, it is said that the fiber is a single mode fiber. I don't know where from this magic number has come, but there must be definitely some papers in the literature which might be giving this number derivation and all. So here, in case of conventional optical fibers, what we have here is a uh, uh, refractive index, the radius of the core. At this, instead of this, where is the pointer? Yeah. So instead of this, we have radius of the core, and this NCO is actually the core refractive index, and N effective is the effective index of the cladding region. So this is called as numerical aperture, as we all know, and this part is 2 pi rho by lambda in case of conventional optical fibers. So if you look at this expression, you can see that since 2 is fixed, pi is fixed, radius of the core is fixed, and N1, that is core refractive index is fixed, and cladding refractive index is also fixed in case of conventional optical fibers. So it's only wavelength on which this V number depends. And as the wavelength goes on decreasing, if you take smaller wavelengths, then in that case V number will be higher. So when this V number becomes greater than 2.405, then the fiber becomes multimoded. Now in this case, what happens in case of photonic crystal fibers, what happens is effective index actually decreases with wavelength in most cases. The effective index decreases with increase in wavelength. So this part is also variable. So as you go on increasing lambda, the numerator is actually is also changing. You are increasing or decreasing lambda. So what happens is it is possible by careful design in case of photonic crystal fibers that the fiber remains single moded for entire range of wavelengths. This is called as endlessly single mode. So it is possible to have endlessly single modedness in case of photonic crystal fibers. Then if you look at this graph, so this is the expression for dispersion. And if you look at this graph, in case of photonic crystal fiber, just by changing the parameters, there are so many parameters to play with now. In case of photonic crystal fibers, in case of conventional optical fibers, you have only core radius, then you have you call it refractive index. You can have different materials. There are very less geometrical properties which you can play with to alter the optical properties of the fibers. Whereas in case of photonic crystal fibers, so many properties like the diameter of the hole is there, then the distance between the holes is there, then the core radius is there. So there are many optical properties. Now by changing these geometrical properties, the optical properties can be tailored. Especially dispersion, if you can see that this is a graph which shows that when you are changing the fill factor. Fill factor is nothing but the core diameter, the hole diameter and the pitch. Pitch is the distance between the two holes. So it is the ratio of hole diameter and the pitch. So if you change this fill factor, you see that the zero dispersion wavelength is shifting from left to right or right to left if you change this fill factor. It is possible to tailor the zero dispersion wavelength for an optical fiber. And effective area is one more property which is actually dependent upon all these geometrical properties, and it is possible to have this effective area smaller to have a higher nonlinear property. We'll see that in next slide there is gamma, which is nonlinearity, and it is dependent on effective area. Now I come to one of the most important slides, which actually helps us to select what material we have to use for designing a photonic crystal fiber. So there are so many materials, and definitely there is silica over here, and silica is actually one of the most useful material which is used for designing the optical fibers, because the reason is obvious that the transmission percentage in case of silica is very high in comparison to other materials, and generally the transmission window for silica remains 1.55 micrometer or 1.31 micrometer, and this is because of the transmission windows which are there in telecom domain. Now you must, looking at this graph, you will understand that why mostly the communication using silica fiber happens at 1.55 micrometer or 1.31 micrometer, because silica fibers, they offer minimum attenuation within this wavelength range. Now there are other materials also which which are advantageous in other cases, but not in transmission percentage. Like fluorides are there, sulfides are there, selenides are there, chalcogenides and tellurides are there. But they are very lossy when in comparison to silica. So highest transmission percentage is there in silica, fluorides, then sulfide, then selenide, and then telluride and all. But where they are useful, let us see. Yeah. So in case of nonlinearity, you can see that silica is somewhere over here, and other materials which we saw that they are having less transmission percentage, but they have higher nonlinearity in comparison to silica. Basically, this N2 is nothing but the nonlinear refractive index, which we saw in one of the previous slides here. So you see that N2 is over here. So nonlinearity, if you want higher, then N2 has to be higher. N2 is nothing but nonlinear refractive index. So it has to be higher. It is directly proportional. That is directly. So if we want to have highly nonlinear photonic crystal fibers, then we would like to select materials like telluride or selenides or other soft glasses like lead silicate and all. So you see that silica has almost lowest, then fluoride glasses are here, then other short glasses are there, then bismuth glasses and telluride glasses, sulfide glasses and selenide glasses. So if you want to have more nonlinearity, then you will have to select the materials accordingly. Here you will have to see that the transmission percentage also has to be according to what application or what length of fiber you are going to take. What frequency? Yeah, so that is one of the application. That is one of the application. Now look at the kind of photonic crystal fibers which have been already fabricated. So these are different designs which you can see that there are already existing and people are creating. So it's all about your creativity and what you are able to fabricate. You can think of and you can create that design. Now, all these designs, you can see that they have different kind of holes, and then shape of holes is also there. Then pattern of holes is also different. So they are actually designed for different applications. So based upon those application, what application you are designing, what material you are taking, what kind of fiber you want to create, all those things are taken into consideration when you are creating a photonic crystal. Right. So coming to what we are doing with the photonic crystal fibers. So we design optical fibers for three major applications. One is nonlinear applications like supercontinuum and all. Here you can see what we were just wavelength is there. The laser is at the input, and then so basically this application is called as supercontinuum generation, where you have a monochromatic source of light at the input, and then at the output you get a white light. Then second application that we do is OAM generation, which we are doing in OM propagation that we are doing in case in our BRICS project. So we are designing optical fibers which are capable to propagate multiple OAM modes. And so far we have got success of about 300 plus OAM modes in a specific design of fibers. It is not published yet. It is already in communication. So maybe we'll be able to share a paper if you are interested. after some time based on that. Then the third application that we do is sensing. We do SPR sensing using photonic crystal fibers, and this is uh, diagram which is here in case of which is used for sensing. Now, what we are doing actually here is that in optical fiber, there is some metal which is deposited upon the fiber, and then the analyte is placed over that, and depending upon how much light or what wavelengths of light are propagating, it changes with the change in analyte. So this can be used for various applications, like we have published papers for cancer, we have published papers for chemicals and different analytes. We are also working, and recently 2 days back only we have got one. I was discussing with you. We got one project also, which is sponsored by our own group for this sensing. So what is happening is when the light is propagated in the core, at certain wavelengths, this SPR mechanism happens, and then if the analyte is placed on that metal layer, then the properties of the light which is propagating in the core, they change with the change in refractive index of analyte. Because we will see that in one of the. So what is happening here is in this diagram we see that there are refractive indices. Different refractive indices and one confinement loss. So confinement loss is actually the loss which the light experiences when it propagates through a fiber. So we see that at this particular point, these two are the confinement. These two are the refractive indices of core region and the SPP mode. So this is core mode and this is SPP mode, and this is the confinement loss. Where these two are crossing each other, we see that the confinement loss is maximum. So what is happening here is, I go to previous slide, this one only. So what is happening here is, this was the core, and this light, it was all it was all coupled with the metal region or the sensing region, and there is no light in the core. That's why confinement loss is maximum at this point. So PCF advantage is that, as I have already told you, that there are so many designs possible, and based upon these so many designs, there can be different sensing properties or enhancing of sensing properties can be achieved using PCF. This is a typical setup for experimental setup for SPR sensing using PCF. So you can see that there is a light source, there is a PC, and then there is a sensor which is coupled, which is connected to light source and optical spectrum analyzer, and we see that there is a shifting of wavelengths of the light which is connected to these this sensor based upon the change in analyte. Now this is one of the most important part. Besides the design of PCF, there are also other things which have to be taken into consideration. So the plasmonic material, you see that there is a plasmonic material outside, a metal layer which is of gold in this case, which is deposited outside the fiber. So this is a typical design, and there is a plasmonic material, and then there is analyte which is laid over this plasmonic material. So what is actually happening is that the PCF, you fabricate it, you deposit the plasmonic material around it, and then you dip it into the analyte. That's how the sensing. So that's how this analyte will be all over the plasmonic material. This is another design of the PCF which is used for sensing. Now there are different materials which are used for this, like gold, silver, copper, and aluminium. Now they have their own advantages and disadvantages. Gold is very common. It exhibits a strong stability in case of aqueous environment, and then there is large shift in resonance peak, whereas the silver, it shows narrow band uh, uh, resonance peaks, which means that it is possible to detect even the smallest changes in refractive index of analyte. So it is very conductive and its optical losses are less. But the main disadvantage of silver is that it is susceptible to oxidation in aqueous environments. There are other materials also like copper, aluminium. Nowadays, there is a trend of using a combination of materials like there is a gold layer and above that there is a TiO2 layer, or there can be a graphene layer and other combinations. So graphene is there, and then there are indium ITO also, which is nowadays being used for SPR sensing. Now, second thing that we have to take into consideration is that it is possible to have internally coated plasmonic material or externally coated plasmonic material. So you can see that internally, in case of internally coated plasmonic material, you see that the whole PCF is outside, whereas these holes are being internally coated. Like in this case, you see that the gold is here coated inside the holes. Then in this case also you see that the gold is coated inside the holes. So these are all the designs which have plasmonic material which is internally coated. This is very difficult to achieve. So most of the practical designs use externally coated PCF sensors, where the sensing region is outside the PCF and the plasmonic material is somewhere over here. So in this case also you see that the plasmonic material is externally coated, that is outside the fiber. Now there are other designs also. This is one of the most practical designs which have been which are being used. That is called as D-shaped PCF, where you take a normal PCF and it is actually side polished, and one of the region is made flat and it is brought close to the core so that the light gets easily coupled to the plasmonic material, and that's how happens. There are other ways of doing this also, that instead of removing it from one side, the material for a particular length, it is removed from all sides, and then the gold nanoparticles are deposited over that. So these are some of the designs and their comparison. There can be selectively metal coated. There can be internally nanowires filling. There can be D-shaped. Microfluidic slots are also there, and external sensing approach. Most of these designs are actually simulated and modeled. But this particular D-shaped, this is actually one of the most practical designs which can be used for SPR sensing using PCFs. This is one of the PCF which we have designed for. This is our own indigenous PCF which we have designed, and when we actually designed, we designed it for some other application. Actually, we designed it for supercontinuum generation. It was actually, the idea came way back in 2011 when I was visiting City University, and there they designed one equiangular spiral PCF, and this structure is it looks like equiangular. It does it is, but having 8 holes. Equiangular has somewhat uh, uh, holes which are not in straight manner. They are equiangularly spaced, like placed. Like one hole is here, then its adjacent hole will be at another angle, and then the adjacent hole to second PCF will be at another angle. So it goes on rotating like this. So this PCF we were able to fabricate with the help of our partner in the BRICS project and in Russia, and they have their own drawing tower, and they fabricated it like this. So you can see that the fabricated PCF is there, and they also characterized it. We published a paper also. We have also done modeling of SPR sensor using this particular design. You can see that the spiral PCF is there, and then gold is deposited over it, and then SPR properties have been analyzed for this for sensors. So basically, what we look at when we design a PCF-based SPR biosensor is the design should be practical and feasible. See, in case of simulation tools, you can model anything, and whatever you do, it will give some output or other. But whether it is practical to fabricate it or not, this is important. So we take into consideration that whatever we design is practical and feasible. So we just don't do random designing and then see what is the output. And for this, you need to collaborate with some people, or you should visit some drawing tower and discuss with them that what are the things that make a particular design practical or feasible. There is one fabrication facility, PCF fabrication facility in Jadavpur University. I think CGCRI is having that. India. There are several other facilities abroad, but one is in India. And refractive index range of the analyte which you want to sense. The third thing is it should have a high wavelength and amplitude sensitivity. These are the goals which we take into account when we are designing the PCF-based SPR biosensors. So this is the end of one part of my slides. This is presentation contains this presentation contains images, information, data from various internet sources and papers. I would like to acknowledge all the reports and content taken from their websites. I would also like to thank for giving this opportunity. Actually, this lovely country I used for some other country. I have used same sites for some other country also. I was visiting Korea at that time, and I gave this presentation first at that place. The university name, but somehow it remained. But this country is also beautiful. I would like to acknowledge NSE talk. Thank you very much for this talk. I know that it is very difficult to give all the information in limited time, but I tried to convey whatever I was able to do. But if any one of you is willing or thinking of doing something on PCFs, then we can do it together. I'm very much open to collaboration with anyone. You may be a student, you may be a teacher, you may be a researcher, you may be in industry, whatever capacity you are, all those who are online. Also, I'm very much open to collaborations. We have multiple collaborations like Dr. Ghanshyam Singh. We are also collaborating together for different projects, almost all the projects. If you see last 35 papers, we are all collaborating on all those papers. Next part of my talk is career related, and this talk also I gave on one of the international forums, and this is about making a stellar career in optics and electronics. So why I have selected this particular topic is as Honorable Vice Chancellor sir was also mentioning that in coming time you'll see that optics and photonics will be everywhere. Electronics has its own limitation. Dr. Ghanshyam Singh was talking about that, and uh, sooner or later we are going to see that there will be unprecedented growth in optics and photonics domain, be it communication, be it computing, be it anything. So basically, when we are talking of optics and photonics, right now we see that this is something which is specifically about physics, and sometimes we as an I also used to think like that. I am basically an electronics engineer, and I used to think that why should I go, or why should I go into this domain which is uh, more of physics and less of electronics and all those things. But I found this very interesting, because whatever we are creating in this is actually related to electronics. We know that the communication is integral part of electronics. Electronics and communication stream is there. So communication, optical fibers have already taken over the communication part, and very soon we'll see that computing will also be taken by photonics. So it is not wise to remain in a field because just because you started from there and you want to remain there lifelong. लोग अपनी growth के लिए we keep on changing our fields. We keep on upgrading ourselves. This is called as upgradation. So first thing is that whatever you do, just see that how it is going to look like in say next 20 to 30 years. You are still very young. All of you are maybe in your maximum 30s or 20s. So you need to upgrade yourself, and optics or photonics is definitely a good career choice. Nowadays we are hearing about so many things, but this is something which is going to be the technology of future. So choosing a right career path is very difficult. Sometimes we do not know what to do because there are so many things which are happening around us. We sometimes see that AI is there, and should I go in AI? Should I go in robotics? Should I go in IoT? Should I go in cloud computing? Should I go in VLSI? Should I go in communication? Should I go? I mean, it's all very difficult. We do not understand that sometimes it is very difficult choice. कि किस में जाना चाहिए. So there is a lack of clarity which is there that we are not able to choose a right career path. Similarly, there is also a fear of failure. Sometimes people think that should I go with the industry? Should I go with academia? Should I go in research? Should I go for a startup or whatever? So there are a lot of things which are there, and sometimes we see that people are not doing well in startups, so we should not go there, or people are not doing well in industry, so we should not go there, or people are not doing well in academia, so it's very stagnant, so we should not go there. So there are a lot of things which we see around us, but that is a very important thing which stops us from doing the things. There are personal circumstances also. So I see people going to industry, whereas they always wanted to go for higher studies, but they go to for a job just because of their family conditions. Sometimes I see people from industry coming to academia because of their personal reasons and all. So there are personal circumstances also. We do have sometimes limited information, and there are so many career options which are around us, and we see that sometimes there is a person doing well in something, and we think of becoming like that, or a person doing good in some other thing, we want to become like that. So there are so many things which really stop us from taking decisions related to career. So if I talk specifically about optics and photonics field, these two things they are two different words, means there must be some difference also, but they are almost very similar, like these three bulbs that you see. One is fluorescent bulb. So they are very much related. Optics and photonic technologies, basically they are dealing with the emission, processing or detection of light. We have already seen that in case of our technical presentation. There almost all few of them were there. This includes the spectrum ranging from far infrared to X-rays. So as Honorable VC sir was also talking, that this spectrum is very large and free. Next is who can get into optics and photonics. It's not limited to electronics or physics people. There are several other different domain people who are into optics and photonics, like physics graduate, engineering graduates we have already talked of. Applied mathematics graduates can get into this. Material science graduates can get into this. Chemistry, biology, biomedical graduates, computer science and engineering graduates. Everybody, almost everybody, even mechanical I have not included, but mechanical can also get into this. It's very similar to like can get into an IT company, and anybody can get. Basically, this is the stream which brings brightness. So, as the slide itself says that light brightens life. So there are so many applications that you can see that they are based on optics and photonics, like AR, VR, imaging, display, lighting, machine tools, quantum, scientific tools, security. PC sir was also talking about security, that security is one of the major features of quantum technologies, and quantum technology key enabler is photonics. So security also is there. All these areas, all these things are governed by optics and photonics. So there can be several options like pursuing the bachelor's degree, which you have already, most of you have already started or finished. In optics or photonics and related fields, if you are into electronics and communication, you are very close to it. You can do a project related to optics or photonics. There are a lot of opportunities because this area is still in evolving phase. And we know that what is going to come 20 years later, as Professor Singh was also mentioning, that it is growing like anything, following Moore's law actually. So gain a fundamental knowledge and skills in optics and photonics, explore specialization areas like optical engineering or laser technology and photonic materials by doing project at UG level, or if you are at master's level, then also you can do a project on this. Even if you are in fields like VLSI or other things, you can do a project related to optics and photonics. Continue to master's or PhD degree, which is definitely depends upon you, whether you want to. If you are already into it, no problem. If you are not into it, it's optional. You can go for higher studies in optics and photonics. So in case of optics and photonics, if I talk of, there are several options, career options, like academia, R&D, industry, entrepreneurship, consulting, applications, and system integration, technical support and training, and sales and marketing. All kind of career options which are there in any field, they are also. So yes, there is a definite option. Those who are doing masters or those who intend to do masters or PhDs, there can be an option whether you want to go for academia or you want to go for industry. So it depends on your own preferences or goals or priorities. And these preferences, goals, and priorities, they keep on changing. So it's like sometimes people who are in industry, they want to go in academia, and when they are in academia, they want to set up an industry. So all those things are there. You must be already knowing that there are so many industries which are later on acquired by giants. They actually started as a startup in different universities. So that those priorities and goals keep on changing. Both academia and industry offer unique advantages, and individuals should consider their own aspirations and values when making career decisions. So there are two comparisons which you can see in this slide. In academia, it is intellectual freedom, autonomy, flexibility, whatever research I want to do. Nobody is forcing me to do this research. You are in industry, even if you are in research, you are told that you have to do research in this. Here in academia, whatever I want to do, I am doing. If I want to change it, I can change it on myself. Collaboration and networking, like we keep on attending conferences and workshops and seminars, and there are a lot of chances to network with the people, meet great people like you, and visiting great places like this. Whereas in industry, you talk of that your time need. No time. I don't have industry people for a conference in person mode, and you'll see that actually they do not have time. They are not see they are not having time because they have a lot of other priorities, because industry has to cope up with the competitors. If you don't do it, somebody else will do, and you will be out. So that is there. We get a lot of chances to do this. Personal and professional development, teaching and mentoring, intellectual stimulation, long-term impact, funding and grants are there, prestige and recognition is there. Whereas industries, they have their own advantages, like immediate application is there. Whatever they do is applied to the market immediately. Whatever we do comes after 20 years or 15 years or 10 years. That's what academic research is. Whatever industry does, it comes into immediate application. Competitive salaries and benefits, rapid career progression, collaboration and teamwork. Actually, all these things like salaries and other things, they are personal choices. It's not that everybody who is going into industry actually wanted to go in industry. There are several people who want to go for higher studies, but due to their family requirements, they go in industry. So there are several other things. Rapid career progression is there. Collaboration and teamwork is there. Access to resources and infrastructure, exposure to industry trends. Then there are practical skills and training opportunities. There are industry-driven research and development opportunities, and definitely entrepreneurial opportunities are there. You see that there are so many entrepreneurs who worked for a particular company, and then they moved out and set up their own industry. So all these opportunities are there with the industry. So based upon whatever you want to do, what are your preferences, you can make a choice between academia or industry. Well, this is one of the favorite slide which I show to in most of the career development. So it's actually you who has to craft your career or your life. As you can see that there is a piece of rock, and it is crafting itself and becoming a beautiful personality. So similarly, you can build your own career also, that which career path you want to take. According to that, you can start building, and this is the right time. So if I want to go in industry, see that what industry is looking for. I started doing those things. I started learning those things. If I want to go for academia, then I'll start preparing for GATE or GRE or whatever. If I want to go for say masters or something else like MBA or other things, then so it's actually the right time when you are in second year or third year or pursuing your BTech, that you can start building your own career. Or so start preparing your profile for that. The CV should, what an industry person is looking at a CV, just highlight those things, that these are the things which they are looking for. Then start gathering that expertise or knowledge. Highlight relevant coursework you have taken, and such as optics, photonics, or lasers, or electromagnetism, or quantum optics, or optical engineering. because this is related to optics. So I put optical related subject. If you want to have a different thing, then you just highlight what subjects you are doing for those things. So take projects or research that are directly related to optics and photonics. Why I'm talking about research so many times? Because you see that industry is also looking for creative people. They are not just looking for coders or troubleshooters or all those things. They actually look for people who are creative. And this doing research is not publishing paper or uh, publishing patents and all those things. It is actually a training phase which you undergo when you are doing research when you are in your masters. So how to carry out a research? If you have learned in a particular area, then you can do research in any area. If I know how to do research in photonics, I can do research in VLSI also, or I can do in research in quantum. Whatever. Basically, it is a way of learning how to do research. To undertake project or research that are directly related to optics or photonics, try to gain hands-on laboratory experience. Learn to use specific techniques, instruments, tools, or experiments. Nowadays, there are so many workshops which are happening at different places. If you look at the website of all IITs or NITs or even like this, there is a workshop happening here also. So those interested people, they should go and try to attend those workshops and try to learn those tools. So suppose I want to do, I want to go for a communication related job. I mean, this communication systems related job, because communication for humanities people, it means different. So if I want to go for 5G communication, then I'll see that where 5G equipments are. I'll try to attend those trainings. So in that way, you can actually choose the places where you can go and have the training on equipment or instruments or machines. Learn to use industry standard software used in optics and photonics, such as ZMax, MATLAB, LabVIEW, COMSOL. COMSOL training you are going to have in this particular workshop, and numerical also. Develop technical skills like optical design, optical system characterization, laser alignment, optical testing, data analysis, or proficiency in specific measurement techniques. Do industry-related projects and internships during your studies and highlight your contributions, outcome achieved, and any skills or knowledge gained in optics and photonics field. So it applies for any field. I'm highlighting optics and photonics. You can just think of whatever going on in your mind. Join the activities, participate in optics and photonics societies such as Optica or any other, and demonstrate your commitment to the field. Get involved in activities, responsibilities, or attend conferences and events. Publish research papers or make presentations at conferences related to optics or photonics. Those who are already in masters and PhDs should try to attend maximum conferences that you can in your own area, specifically your own area, not for tourism. भाई मेरे को कन्याकुमारी जाना है, विवेकानंद रॉक जाना है. So don't attend the conferences for this. Try to attend the conferences which are in your specific area, where you'll present your papers and get feedback on what you're doing. Meet people who are already working in those areas and get information about what you are doing right and what you are doing. Develop technical skills, optical design software, optical testing techniques, and transferable skills such as problem solving, critical thinking, teamwork, and others which are related to optics and photonics industry. Networking and industry connections. Actively seek networking opportunities within the optics and photonics industry. Attend industry conferences. There are a lot of industry conferences that are happening in Delhi. I always look for those conferences which are happening in somewhere in Greater Noida. There is one exhibition. So I always try to find out that what industries are coming there, whether they are of my interest or not. And if they are of my interest, then I go. Maybe related to the purchase for equipment, or sometimes whenever I'm getting stuck in some problem, so I go and see how they are doing it with their instruments and all. So try to meet with those people. Optica can play a big role in all these things. Those who are actively doing research or thinking of doing research in field of optics or photonics, Optica is something which I recommend that you should join first. It's joining Optica doesn't cost too much. For Indian students, it is $10 for 3 years. So first thing that you get without doing anything is 3-year membership, which you can highlight in your CV. So professional membership column, which used to go empty in your CV, now has Optica member. Okay, this is the first thing that you get without doing anything. First thing. Second thing, Optica, after becoming Optica member, there are a lot of things which benefits that you get. You get a lot of opportunities to apply for different types of grants. Those who keep on attending conferences for Indian students or for Indian researchers, Optica conferences nowadays are free. You need not spend even a single rupee or dollar to attend those conferences. Registration is free, which is normally $500 or so for all those who are full paid participants. So this is second advantage. $10 for 3 years. If you attend 3 conferences, you have actually earned $1,500. Actually earned. Money saved is money earned, yeah. So, so second thing is attending Optica conferences is free. Sometimes we think that going to US and attending those conferences or going to Europe for attending those conferences, it will cost too much and all those things. There are many conferences which are happening in hybrid mode like this one. So again, going there is not a problem. At least nowadays it is happening in hybrid mode. Earlier it was in online mode only during COVID period. Now is happening in hybrid mode. Whenever, till the time it is like this, take advantage of that. So this is a second advantage. This is an individual advantage I'm telling you. There are several other advantages when you attend, when you join your student chapter. So where there is no student chapter, they can just join Optica and take all these advantages. If you have a student chapter, join it as soon as possible. If you have taken only membership and not joined it. So there are other opportunities also. For example, you get 50 downloads per year for I think 50. It's 50 now. So 50 downloads per year. Any paper you can download from Optica website. And there are a lot of other advantages, like once you become a member of such forum. So what is happening is 50 is a limited number, but I have several friends who have 50, 50, 50, 50. So join their group, join a group. In your student chapter group also, only you can have unlimited capacity, 50 students into 50 papers, 2,500 papers. In your whole life, you'll not be able to read. Yeah. So there are disadvantages there. Then there are several grants also, several scholarships also. And let me tell you that almost every year, at least 2 or 3 of my students, they go abroad, sponsored by Optica, to attend a conference. Every year, at least 2 or 3. This year also, with your chapter advisor, one of my students is also going in FIU. You are also going there, no? Denver. So that is all sponsored by Optica. You are going. You are going. So you know Akshat. He was telling me that somebody from NCU is also going. So okay, you are that girl. So there are these advantages also. And at least 2 students or 3 students every year they go. We have SPI chapters also, so the benefits get multiplied. So this advantage is also there. Scholarships are also there. So what you get when you go to attend a conference abroad, you get to meet so many people. You get to meet so many industry people, research people. So what my students generally do, they focus on networking. So whether there are opportunities in their labs for masters or PhD or all those things. So they get all those opportunities when they are going to attend those conferences wherever they get a chance. So this is there. Then there are other advantages also, like a scholarship. One of my student got a scholarship of about $3,000. That was through SPI actually, not through Optica, but all these are there with the Optica also. There are several prizes for those who are doing good research in case of optics and in field of optics and photonics in different areas. So they are also recognized by Optica, and those prizes are there. There are other opportunities also, like representing Optica at different events, like your chapter advisor is Optica ambassador. I am also an Optica ambassador. Professor Singh was DLP, distinguished lecturer. He was there with IEEE Photonics Society. So there are different chapters. And let me tell you that Optica is one of the societies which gives maximum benefits directly to its student members. There is no other society. I'm a member of more than 10 societies right now. IEEE Photonics Society, IEEE Broadcasting Society, IEEE Communication Society, Optica, SPI, and several others. So at least 10 I'm a member. I sometimes forget that but still, I find Optica is the society which gives maximum benefits to its student members as well as all kind of members. There are a lot of opportunities. And for at all levels, like at my level, what I enjoy with Optica is networking chances that I get when I visit places. This is one program which you can attend at Optica. Registration fee is about $500, which is about this is all paid flights, meals, accommodation in US. This happens generally in US. Chapter advisor has attended it. Innovation School. If you have a startup idea, then you can join this. This is a 5-day school. I attended this in 2020. This is a great. There are several fellowships and scholarships. Some of them are listed over here. Polyakov, Stoichkov, Bonafnant, Corning Women, Optica Women Scholarship. There are two specific scholarships for women. There are different travel grants also, like Corning Women in Optical Communication, FIOLS in Cubic, Milton Cheng Travel Grant, Clio in Cubic, Milton, and so on. There are several. There is Optica Student Leadership Conference, which happens. You are going there. FIU, it is happening with the FIU. So this is happening generally in September or October. Generally, it is co-located with a big conference. There is a portal which is specifically there for optics, those who want to work in optics or photonics. There is work in optics, and you get a free access to log into this portal and see what are the job postings which are available in all parts of world, specific to optics and photonics. And this sometimes includes postdoc opportunities also. So this is one salary survey which was done by, which was published in one report. And you see that this is what people answered, that where they got into their present job, how they got into their present job. And you see that the largest pie is networking or referral. So networking opportunities are great, and they sometimes give us good opportunities to land up in good job. So all these are different advantages or benefits that you can avail through joining Optica or any other technical society, but Optica is the one which has maximum. This was my last slide. Thank you.